Hi, in this video we're going to do multiple regression using JMP. I'm going to start off by opening a data set called body fat. The goal in this situation is that we are trying to accurately measure body fat. Now, to do this properly, you need to do a big water displacement take, and you need to accurately measure somebody's body density, and then you can assess what their percent body fat is from their density and the size of the rest of their body. That's very expensive. The problem here is to try and predict body fat just by knowing somebody's age, their weight, their height, and being able to do a bunch of simple measurements that you can do with any measuring tape on your own, and to see whether you can therefore then accurately predict body fat just on these measures instead of having to go do water displacement or fat calipers or those sorts of things. So let's start off by running our model here. To do a multiple regression in JMP, you come up to Analyze and you come down to Fit Model. Select your response. In this case, we're trying to construct a prediction model and find the important features predicting body fat. So that is our response. We then can come and select from all of the explanatory variables, and we will in this case select all of the other variables and put them in as potential covariates or explanatory variables. We only want the minimal report. We don't care about all the other information. We just want the quick report on this regression analysis. What we're going to do here to construct this model is actually do backward selection instead of forward substitution, and that's not uncommon when you have this many potential predictors. Using forward substitution, there are many different possible models you could start off with. In this case, we're just going to run and do backward selection, and you'll see how quickly we can do this by sort of manually. So here we say now run model, and we can see the full model with all of these possible predictors: wrist circumference, forearm circumference, knee circumference, abdomen circumference, and so on, people's height, weight, age. Knowing all of that information allows us to predict about 75% of the variability in somebody's percent body fat. So there is still some additional either noise or components of somebody's body feature that helps to contribute to their body fat that we aren't measuring in these other by knowing these other features of their body. But we want to find the most important things that we can measure to help us predict body fat. So instead of measuring all of these things, there's some we can drop without really affecting our model. So we'll first off start off by finding the least important covariate, that is knee circumference. It is very clearly not significant, so we're going to try running this model without that covariate. And you can see up here, remember, the full model with everything we know about this person predicts just under 75%, so 74.9% of the variability in body fat is predicted by this full model. Now we're going to run the same model, but take out knee circumference, run the model. Okay, we're still at 74.9%, but now you can see there is no more knee circumference in our model, and so we'll go ahead and remove the next least significant predictor, in this case, chest circumference. Still, 74.8% of body fat is explained by this model. And now we've lost two of our covariates. Now I'm just going to proceed in a number of steps in removing other unimportant covariates. So in this case, now height appears to be the next least significant. The model without height now still over 74% of the variability explained. Next in line to be removed is ankle circumference. So again, this is saying knowing somebody's ankle circumference while knowing all of these other variables doesn't add any additional information. Next, it looks like bicep circumference. Notice, well, I'll just remove bicep circumference first here. Next least important appears to be hip circumference. We're getting down there to the nitty-gritty. There's only a few variables still important. Notice now that the only one that is insignificant is neck circumference. Let's see what happens when we remove neck circumference. Now it appears that thigh circumference has become insignificant. It appears that there probably is some collinearity between thigh circumference and neck circumference, but we still have a lot of predictors in our model, and we're still over 74%. So we've removed a bunch of variables already, and we still haven't reduced the ability of our model to explain the variability in body fat. So these were clearly not adding anything important. So now we'll remove thigh circumference, and now age has become very not significant. this could be concerning if we had reason to include thigh and age in our model, but in this case we are still predicting the reduction in the explained variability is very small, so we'll just go ahead and remove age at the moment because it appears that we still have a very good model for this prediction. And now we have only very important predictors, very significant predictors, and we still are explaining over 73% of the variability. So we've only lost just over 1% of the variability explained by reducing the model to only 4 measurements. This is essentially saying that if we can measure somebody's wrist circumference, their forearm circumference, their abdomen circumference, and their weight, we can predict with some confidence their body fat percent. Now, as with all regression analyses, we do need to check the assumptions, and we can do that again with the residuals. But you see there's no option to just plot the residuals as there was in the simple linear regression. But we can do that easily by just saving the residuals in a column in our spreadsheet. Residuals. And now if we go back to our, the data sheet, you can see that at the end where we had all these covariates, now we have residual body fat as yet another column in our data set, and we can look at the distribution of those residuals. Residual for body fat. And this is checking the assumption that the residuals are normally distributed. They do appear to be about approximately normally distributed. The peak, the mode of the distribution is near zero with steeply declining symmetric tails in either direction, so that's one assumption verified. The other 2 assumptions we can check with our standard residual plot, but what do we plot residual body fat against in a multiple regression setting? That is also easily accomplished. We can take our final model, here it was, and we can save something called the predicted values. Remember, the word predicted value is the same as saying fitted values, it's the same as saying estimated conditional mean, it's the same as saying all the points along the line. So we're going to plot every predicted value, every y hat for each combination of the x's. So remember, this is our estimated body fat, predicted body fat, fitted value, predicted value, all means the same thing. This is what our model says the body fat should be for somebody with this wrist circumference, this forearm circumference, and so on. To check the assumptions, we want to do our typical residual plot, but we do residuals versus these predicted values. We'll see the plot here in a second. Let's fit the mean to this, which should be 0, right down the middle. And you can see that it looks like the remaining 2 assumptions for our regression are valid. We have constant variance across all the different values of the predicted body fat, and we have no obvious patterns in the data. And remember what this is saying. Remember, the predicted body fat are all the points that in the simple linear regression would have fallen along our line. In this case, since we're doing multiple regression, all of the predicted points are those on the plane or the hyperplane. So these are all the predicted points, and so you can see that the residuals for small values of the predicted are widely distributed around the mean of 0, and they're also widely distributed for large values of the predicted. So everywhere throughout the hyperplane we have some randomness of the residuals, and this appears to be a valid regression, and we can say that these 4 explanatory variables are the best way to explain body fat using the least number of measurements. So if you have any questions or you think I've left anything out, please add it to the comments.